In this video, we're going to be tackling a Unit 4 AP Physics 1 FRQ. So, show all your work for each part of this question. The parts within the question may not have equal weight. So, a lab cart of mass m is free to move to the left or right on a straight horizontal track as shown in figure 1, with negligible force in the axles of the cart wheels. The cart is at rest at time t is equal to 0. A single horizontal applied force, which may or may not vary over time, is then exerted on the cart. Figure 2 shows the resulting momentum of the cart as a function of t, where the positive direction is taken to be toward the right. The momentum reaches a maximum of p max at t is equal to t1. So, what we can do is, so for this question, we essentially have the relations p equals to mv for momentum. We have F is equal to dp over dt, and we can rearrange this to V is equal to P over M. So, what it wants us to do is to draw the forces at T is equal to 0.9 T1 and T is equal to 1.1 T1. So, we first have to identify the forces that are acting on the cart. So again, the cart is on a horizontal track with negligible friction. So that means that the weights are going to be the weight mg, weight downward, the normal force, and also the applied force from the push. So what we do is we have weight mg down, Fn up, and F up horizontal. So we can use the momentum graph to infer the direction of the force. So using F net is equal to dp dt, that means that we have a positive slope. That means that a force is right. If you have a negative slope, so for PT, that means your force is to the left. And also we know that a steeper slope is a larger force magnitude. So at 0.9 T1, this is the time before the peak momentum, right? So before the peak momentum, that means that the momentum is increasing. And we know that the slope of PT is going to be positive. So therefore, the applied force is to the right. So then for this, we can draw G here, and then we can draw Fn here. This is the same. And then then we can, to the right, we have F. Okay, this is a little annoying. That's F applied. Now, this is the time, at t is equal to 1.1 T1, this is the time after the peak momentum. So this is when the momentum is decreasing. Well, actually, let's just write P increasing, PT slope is positive. Okay, and then for this one, we have the momentum P is decreasing, and we have P of T is slope is negative. So that means that the applied force is to the left. Now, relative magnitudes. What we need to know is that the slope of the graph after T1 is going to be of T1 is steeper before T1. So that means, the slope of the graph of T1 is steeper than before T1. So that means that F app is going to be 1.1 T1. And then, hold on. F app 1.1 T1. Yeah, so this is going to be there, F That's 0.9t1. So that means that the leftward arrow should be longer than the rightward force arrow. So that, yeah, this is going to be a little bit, make this a little bit bigger, but it's just bigger. So that was for A. Now derive the expression for delta x, the final displacement of the cart at time 2t1. Express your answer in terms of m, p max, t1, and physical constants as appropriate. So what do we know about the connection of displacement to velocity? Well, we know that displacement, delta x, is going to be equal to the area under the velocity time graph, right? So that's the area under velocity time. But this graph that we have is momentum versus time. We have momentum versus time. So we convert. How do we convert? Well, we know we have the relationship P is equal to mv, and when we see v right here, so v is equal to P over m, right? So that means if we have delta x, we can rewrite this as delta x is equal to integral of 0 to t1 P of t over m dt. That's equal to 1 over m 0 to t1 P of t dt. So then what we need is the area under the momentum time graph. So how do we find the area under that? Well, we can look up here. So the area is, we can see that the graph is a triangle, right? So then we know that the area is going to be 1/2 base time height. So that's 1/2 2t1 times P max. 2 cancels, so then the area is just going to be P max is times T1, right? Now we have to divide the mass to get the displacement. So down here we have delta x of f 1 over m P max T1. So we divide by the mass to get the displacement. So then, well, we can rewrite this as delta x f is equal to P max T1 over m. And then that is it. So let's move on to our next part. Okay. On the grid in figure 4, sketch a graph of the cart's acceleration as a function of t. So, starting from the definition, we know that from momentum versus, we're given momentum versus time, not acceleration, right? So we know we have the relationship of derivative of p dt. So then we can use Newton's second law, and that's going to be a is equal to f net over m. So that's 1 over m dp dt. So therefore, we know acceleration is proportional to slope of the momentum time graph. So we can read the slopes from the momentum time graph. Slope, or let's do this in pink. So we can see that the slope of from t is equal to t1 to 2t1. We can see that from here we see the momentum decreases linearly back to 0. Slope is going to be constant and negative, and this line is steeper than the rising part. So this is for T1 to 2T1, or we'll just do T1 to. So because we know that's the case, right? So we can, we'll just write it here, dp over dt 0 minus p max divided by t1 negative p max over t1. So that means our acceleration is going to be equal to negative p max over mt1. So this is going to be a constant negative acceleration, same, but it's going to have the same magnitude as before. So what is the acceleration graph going to look like that we have to draw? So from 0 to t1, it's going to be a horizontal line above 0, and then from t1 to 2t1, okay, this is a little longer, 2t1. Well, I want to do it like this. So from t1 to 2t1, it's going to be a horizontal line below 0 of the same magnitude. There's a sudden jump at t equals to t1 because this is when the slope changes. So a second cart 2 has a mass greater than the mass m of the original cart and is placed on the same track as shown in figure 5. With cart 2 initially at rest, the scenario is repeated with a horizontal applied force having the same time dependence as the force that was applied to the original cart. Indicate whether the maximum momentum for cart 2 is greater than, less than, or the same as the maximum momentum for cart 1. Justify your answer. So cart 2, we know, has a greater mass and it's going to be the same track. It's the same track, and the same time, and it's going to be the same, same time dependent force, and same force as cart 1. So that means we can use the impulse momentum theorem, which is that J is equal to delta P, and we know impulse, so we just write J is F of T D of T. So what this means is that it depends only on force and time, not mass. So we want to compare the impulses for both the carts. So J2 is going to equal to J1 because it is the same function of force over time, and it's the same duration that you're applying the forces for. So then we know that because both carts start from rest, therefore we know that delta P is equal to P max 2, P max 1. So that's the case. Now address the mass difference. So what? Well, we know from P equals mv. We know that a heavier mass, smaller acceleration, and a smaller acceleration, that's going to mean a smaller velocity, right? Okay, but that's what we know, right? Or not from this. Wait, but then using this, sorry, had it mixed up. Okay, so the larger mass compensates for the smaller velocity because the impulse is the same, right? So your answer is going to be equal to. So the maximum momentum of cart 2 is going to equal to max so they're the same because both carts experience the same impulse. Which depends only on the FA and time interval. Since both carts start from rest, the delta P, and thus for both